Thanks. Hi, everybody. Thank you for coming. Thanks, Asher, for organizing this. My name is Uri. I'm a postdoc here at LTI. And the work that I'm going to talk about was led by Aman, who is sitting over there, Shuyan and Luyu, who are PhD students here at LTI. And it's also a joint work with Pengfei, who is a postdoc here, and Yimi, Jamie, and Graham, who are professors. As you probably know, language models are at their peak of public popularity these days, thanks to ChatGPT mainly. I personally see this rise in popularity as a gradual process, but it feels like it got to such a high level and such a high performance that the broad audience has started to know what language models are and started to using it. But formally, we know that language models are basically functions that assign a probability for every sequence of tokens or words. So if we have W1 to Wn, which is our sequence of words or a sentence, a language model is basically anything that can take this sequence and provide us with a probability. So for example, if our sentence is Barack Obama was the president of the US, a language model might give us the probability of 0.0012. Now, most language models are autoregressive, which means that they decompose the joint probability of the entire sentence into the product of every word given the previous word in the sentence. And this fact allows us to use language models in the way that we use them by letting the language model complete our prefixes or our prompts. So we can provide these language models with a prefix such as Barack Obama was. This is also called a prompt. And we can ask the model to generate the next word, and then the next word, and then the next word, until we can this way generate an entire sentence and get the answer for the question of, for example, who was Barack Obama. Now, this doesn't always work. Let me show you. So for example, this is a model called Bloom, which has 176 billion parameters. And if we give it the prompt of Barack Obama was, it completed with was the first president to visit Hiroshima, and he did so in May of 2016. He was the first, which is true. It's not like it may be true. It can also be completely wrong, but it's not exactly what we meant or what we expected the language model to give us. So a very common approach is to provide the model with few shot examples. So for example, we can write that Hillary Clinton was the Secretary of State of the US, and that Mike Pence was the Vice President of the US. And then when we ask the language model to continue the sentence of Barack Obama was, the language model actually gives us the completion that we expected, that Barack Obama was the president of the US. So basically, by providing the model with input and output examples, we can instruct the model in some way to give us the completion in the format that we want. Okay, it's correct this time, and it was correct before, but this way we can tell the model what kind of answer we expect. So this is called few-shot prompting. So as I said, we give the model several examples as part of the prefix or of our question, and then the model can actually complete the sentence in the format that we want. Now, people have also trained language models of code. Usually there's like the most well-known language models are trained on mostly natural language, but nothing prevents us from training language models on code. One prominent example is the Codex model that was released by OpenAI, and it is also provided as a coding assistant in the IDE that you can install. And if you haven't, I really recommend trying it. It's really helpful. It's a plugin called Copilot that works in your IDE and basically completes your code for you. Even if you think that your code is a snowflake that nobody has written before, it's super useful and really saves you code that you would have written yourself instead. And then a few months ago, Aman was wondering whether are there natural language tasks in which language models of code perform better than language models of natural language. So we want to find natural language tasks that are completely unrelated to code, but maybe the language model that was trained on code has learned some other abilities that will allow a language model of code to perform better in these natural language tasks. So here's a motivating example. One such data set is the proscript data set, where the input is a natural language goal, such as serve the pot pies on a plate. And the output that the model is expected to generate is a graph where every node is an intermediate step in the process of serving the pot pies on a plate. And the edges in the graph are the chronological dependency edges between different steps in the process. So given the high level input, the goal is to generate this graph. Another example is the explographs dataset, where the input is a belief, an argument, and a stance, which is either support or counter. And the goal is to generate this graph, which uses the argument to support or counter the belief. Notice something a bit unique about these kinds of tasks, that these kind of tasks require both the natural language knowledge to we need the model to actually understand what does begin putting pies on a plate means. So the model needs to have a large enough capacity of natural language understanding on natural language modeling, but also the model needs to be able to perform structure prediction and actually generate complex graphs. So these are two abilities that these kinds of tasks require. So the standard approach of addressing these kind of problems is to flatten this graph, this output graph, into a list of edges. So basically any format that allows us to serialize or flatten the graph into a textual format, and then train a model such as train a sequence-to-sequence model such as T5 or BART, or use few-shot prompting using language models as a GPT-3 with the natural language inputs as the inputs and the this flattened format as the output, and expect that the model will be able to generate this flattened graph for our test natural language goals. The problem with this approach is that this kind of format, the format that when we flatten a graph into this textual format, results in kind of unnatural text that diverges from the text that the language model was pre-trained on. Another issue is that locality is a bit different than in natural language. In the general natural language text, for example, in Wikipedia, usually things that are semantically related to each other appear right after each other or in the next sentence. And here, because this text is not actually a natural text, it's a flattened graph. Things that are the same thing, for example, two occurrences of the same node in the graph, must be pushed farther apart from each other, which makes the notion of locality different than in natural language. So back to our question of whether are there natural language tasks in which code LLMs perform better than natural language LLMs, we found that the answer is yes, if you convert the natural language task into pseudo-Python. So instead of representing the output graph as this flattened format of a list of edges, instead we convert the graph into this pseudo-Python format. So for example, we define a class here where we have the goal of serve the pot pies on a plate, and then we define a node for each of the nodes in the graph. For example, take pies out to cool. And then we define the edges as a list that is assigned to the dot children attribute of each node. So basically, we define a pseudo Python code that directly represents the original graph. And then instead of using a model for natural language such as GPT-3, we use a model of code such as Codex to ask the model to generate these Python graphs for our test natural language goals. And finally, when the model generates this Python graph, we can convert it back to the original graph and evaluate it and measure how correct this graph is according to the same metrics as before. So basically, this conversion between graphs and Python classes are completely reversible and lossless. So in other words, we let the model generate code even when the task does not involve code at all. And we call this approach cocogen, for models of code for common sense generation. And we evaluated this on several data sets. One of them is the Explographs data set that I showed before, where the Python format in this case is very similar to the previous format that I showed you, except that we have the inputs of belief, argument, and stance as separate strings here. And also the edges have types in this data set. So the edges that we define in the pseudo Python graph have every edge is a three tuple basically, which has the source, the target, and the type of the edge. And here are some results. Our approach of converting graphs to pseudo Python code is based on the Code DaVinci 2 model, which is the Codex code completion model by OpenAI. And we also compared this to a T5 large model, which was fine-tuned on 1,500 examples. So basically, the main difference between these approaches is that the T5 baseline had seen in its training 1,500 concrete examples, where all the other baselines have seen only about 30 examples in their prompts, because they perform few-shot prompting, while the baselines is actually fine-tuned on orders of magnitude more examples. The other baselines are other language models of natural language by OpenAI, which are different varieties of the GPT-3 model. One is TextCury, which is an older version, and then Text DaVinci 2, which is a newer version that were also designed for natural language. And we compared these, the generated graphs according to different metrics. Some of them measure the semantic similarity between the generated nodes, the text that is inside each node, and some of the metrics measure the graph similarity between the generated graph and the ground truth graph. And as you can see, our cocogen approach performs much better than all the baselines, including where the strongest baselines were both the Text DaVinci 2, which is the GPT-3, and the fine-tuned T5. Here are similar results on the ProScript dataset with this is the dataset with they put the pot pies on a plate. And here again, in this case, the differences were smaller. I believe that the differences between cocogen and the baselines were smaller than before. I believe that the reason is that this dataset is a bit more simple. The graphs are a bit more simple, and the structure is more close to linear than in the previous dataset. So in some of the cases, a textual model such as the Text DaVinci 2, the GPT-3, had managed to predict the graphs correctly as cocogen. Another dataset is more of a reading comprehension dataset, which is called propera, where the input is a paragraph about a process such as photosynthesis. And the goal is to complete this table that shows where in the process does each entity located in each part of the process. So for example, if the input is about photosynthesis, the goal in this case is to fill this table that tells which, for example, for each of water, light, and CO2, where are they located? Are they in the plant or in the leaves, or are they in the sun in each part of the photosynthesis process? In this case, the Python format was a bit different, but it was, but in general, it was, it had the same idea. We defined a pseudo function for each of the steps. For example, the step of water flows to leaf, which is a natural language sentence from the input. We converted that into a function that sets the location of each entity in the function body. And similarly here, cocogen performed much better than the baselines. So why does it work? Why can we take tasks that require natural language input and structured natural language output, but we can solve them better if we convert the input to convert basically the output into Python code? We don't really know, but our hypothesis is that models that are trained on code, that are pre-trained on code, learn different abilities than models that are pre-trained only or mostly on natural language. So here's an example of a completely random piece of code, but let's just see what does the model need to learn in order to generate this green box. So imagine that the model is currently training, and it's training to generate the code that is in the green box. So in order to predict this correctly, the model needs to know that, for example, the stats variable is available in scope, even though it was defined many lines above. It needs to learn that the stats is an array that can be indexed, and the index can come from a shorter distance because it's the I variable that was defined in the for loop, and that this stats is the result of this expression is going to be assigned into ret, and that ret is an array of paths. So the answer should be of type path. So the model also generates this call to get path. So in other words, we believe that training on code makes the model better at some form of procedures or long-range inference, or gets an ability to connect the dots. While a model that was trained only on natural language might have a better natural language knowledge, but it doesn't have this ability of connecting the dots that is required when training a model on source code. Another analysis, so far, there were two main differences between cocogen and the baselines. And the differences are the format that each of them used, whether it's the standard format or the Python format, and the underlying model that we used to query each approach. So the baselines used the textual models, the Text Da Vinci series, and the standard format, while cocogen used the model of code, the Code Da Vinci, and the Python format. But this raises the question of what happens in the remaining cells, right? So here are the results, the BERT score results on one of the tasks. And what we can see here is that if we stay with the Text Da Vinci model, but we just change the format, the increase in accuracy is very minor. If we stick to the standard format of a list of edges, but to just change the underlying model, there is an improvement of 3.5 points. However, this combination of the Python format and the Python model gets us an improvement that is bigger than the sum of each individual contribution. So basically, the key here is to use both the Python format and a model that knows how to generate Python, basically a model that was trained on code. Are there any questions so far? Yeah.
When you train a model with code, does it start from the large language model as long as they're pre-trained with code, or does the objective change when
A good question. We don't really know because we performed all these experiments with the OpenAI models that are publicly available, but we don't know a lot about how exactly they were trained and what was their data. Basically, as far as we think and believe, they were basically trained in the same way. There was probably a pre-training step that basically was trained to just predict the next word, whether that next word is in natural language or in code. There might have been other training steps that are related to instruction following. But what we do know from OpenAI's official announcements is that the the text DaVinci 2 model is based on the Code DaVinci 2 model. So basically every ability that the Code DaVinci model had, the text DaVinci model should have had the same abilities. It may have forgotten some of the abilities, but this model was initialized by this model. So it's supposed to be a fair evaluation, a fair comparison between these two models. Yeah.
So I guess when you transform the natural language to code, I guess like you do some like kind of like manual transformation rather than the language model based. And then like we kind of know that NLP code works pretty well. Have you considered like using this as a kind of like cleanup process so that like you just provide natural language and then have a intermediate step as code and then like another natural language?
It's very similar to what I'm about to talk about next. I just want to answer the first part of your question. In this case, we did have to write these Python formats manually, but we had to do that only for a few examples, only for up to 30 examples. And then we used the same set of 30 examples to prompt every test example in the test set. So it did require a manual work, but it wasn't too bad. Just converting this format, this natural language format to this code format might be performed by a model, but we don't really have a good way to teach the model what kind of format we expect without actually providing some examples. So I think that the annotating manually 30 examples is the cheapest way. Yeah, let's take a last question and then continue. Sorry.
Just for this example, the natural language format actually looks more like code. It looks like a list of variable names. That part of the reason the code model does better.
Right. Yeah, I agree. One of the reasons that it works is that these tasks, it's not a standard natural language to natural language task. It's a task that that gets natural language in its input and output a structured natural language. The key is that the model needs to generate structure.
But I mean, like syntactically, it looks like a list of variable names.
Right.
It could be just the syntax and nothing about the high level from code.
Yes, but models of natural language such as GPT-3, this is the most common way of addressing these problems. So people have found that this format works better than any other way to kind of flatten the graph into text. Basically any approach that you use to flatten a graph into text will have some structure, which is the reason why this works. I'll go into the next part, but I hope you will have time for questions at the end. So far, we showed how, given natural language input and structured natural language output, we can use language models of code to generate code that represent the natural language task. And then we thought that now that we have these generated pieces of code, what additional reasoning capabilities can we get by taking this code and feeding it into a Python interpreter. And we found that one promising application of this idea is this kind of mathematical reasoning problems, where we have questions such as the bakers at the Beverly Hills Bakery baked 200 loaves of bread on Monday morning. They sold 93 loaves in the morning and 39 loaves in the afternoon. A grocery store returned 6 unsold loaves. How many loaves of bread did they have left? Now, the standard approach of addressing these tasks, as you asked, is using the chain of thought approach, which means that we provide the model with few input-output examples in the prompt, which is as before, as we saw in the Barack Obama case, where we show the model a few inputs and outputs to instruct the model what kind of output we expect to get. But instead of giving the model only the final answer to these examples, we provide the model with the entire chain of thought of intermediate steps that a human would perform in order to reach the final answer. So the example at the top is given to the model along with its answer as an input-output example in the prompt. So for example, this example is Roder has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? Instead of just telling the model that the answer should be 11, the chain of thought approach tells the model that Roger started with 5 tennis balls, 2 cans of 3 tennis balls each is 6 tennis balls, and 5 plus 6 is 11, so the answer is 11. And then at test time, given this test question about the bakers at the Beverly Hills Bakery, the model is expected to generate the chain of thought for that test question and hopefully get better final results. There are a few chairs here if you guys want to sit down. The model performs much better at test time because it actually generates its reasoning steps. Now, notice that this chain of thought approach, which is super popular these days, uses the underlying language model for 2 different roles. One role is understanding the question and decomposing the high-level question into steps. But the second role is actually the chain of thought uses the language model to actually solve each such reasoning step. So the chain of thought uses the language model to actually compute how much is 5 plus 6. And recent work has found that even though simple arithmetic can be performed by language models do struggle with more difficult arithmetic and large numbers. So maybe instead of using the language model to do this solving part, maybe we can replace it with something else. So I forgot to mention that even the Minerva paper, they trained a model, 5 billion parameter model at Google on explicit mathematical content. Even they found that after training, the most common classes of mistakes were incorrect reasoning and incorrect calculation, which is another evidence that even if you train a huge model on billions of mathematical tokens, the model still makes arithmetic mistakes. So instead of using the model for both understanding the question and for actually solving each part of the question, why don't we replace the solving part with an exact solver, such as a Python interpreter? So instead of providing the model with prompts from chain of thought, we took every example from the prompt of chain of thought and we converted every sentence into the corresponding Python statement. So instead of just saying that Roger started with 5 tennis balls and 2 cans of 3 tennis balls each is 6 tennis balls, we added a Python statement that represents each such step. So if Roger started with 5 tennis balls, then we added tennis balls equals 5. And if 2 cans of 3 tennis balls each so we added bot balls equals 2 times 3. And eventually the answer is the tennis balls plus bot balls. And then we concatenate the new test question. And we hope that the model will be able to generate the Python program that represents the new test question. Notice that, by the way, in this case, we don't provide the model with the final answer as before. Previously, chain of thought gives the model the final answer of 11 because the model is the one that is expected to perform this arithmetic. But in our approach, we just give the model the Python chain of thought without the final answer. We don't even want we don't even want the model to try to do the arithmetic. We feed that to the language model with the new test question, and we hope that given the test question, which is in this case the question about the bakers at the Beverly Hills Bakery, the model can generate the Python code for the test question, and eventually generate that answer is loaves baked minus loaves sold morning minus loaves sold afternoon plus loaves returned. And instead of expecting the model to generate the final answer, we just take this code and feed it into a Python interpreter, and we get the final answer of 74 from the Python interpreter, not from the model. So in other words, instead of teaching the model to solve the question, we are teaching the model to write a program that solves the question when it is fed into the Python interpreter. And we call this PAL for program-aided language models. I see a few questions on the chat. Let's see if they're about this part. Okay, Shuyan, who is one of the leaders of this project, has already answered. Okay, so we evaluated this on a variety of datasets. One of the most popular datasets is the GSM-8K dataset, which is the dataset that these examples about the Roger and the tennis balls were taken from. And here are some of the results. So first, you can see that the direct codex, the standard few shot prompting approach that gives the model pairs of inputs and direct outputs, performs much worse than Codex plus chain of thought. So COT is chain of thought. So this shows you this gap between 19.7 and 63.1 shows you the benefit of using chain of thought in general. So this is just in general, not our contribution. The rest of the models are different base models, such as Google's Lambda, Codex, Google's Palm, and Minerva that use chain of thought. One interesting thing here is that Codex using chain of thought performs better than Palm and Minerva, even though Palm and Minerva are much bigger, and Minerva was trained on explicit mathematical content. Another interesting point is that in the chain of thought paper, they experimented with using a calculator. So they had a similar idea of letting the model use a calculator to compute each arithmetic calculation instead of expecting the language model to do the arithmetic. But this gave them an improvement of only 2.3 points, while using PAL that uses a complete Python program and not only a calculator result in an improvement of up to 9 points. And this similar trend appeared across multiple data sets and benchmarks in this family. So every group of bars here is a different benchmark. And in each group, we have Codex that uses chain of thought, Palm that uses chain of thought, and our PAL, which is our approach. And as you can see, in each of the benchmarks, PAL performed better than Codex that uses the same language model but with a different prompting approach, and Palm that uses chain of thought, but it's a much bigger model. We also experimented with another popular approach these days, which is called self-consistency, which is very simple. Basically, instead of expecting each model to generate a single completion, we let every model sample 40 different completions, and then we take the majority. So we let every model generate 40 different guesses or candidates, and we evaluate only the one that is the majority among the different generations. And as you can see, all models improve, and the gap between PAL and the baseline decreases, but PAL is still at least or almost 2 points better than the best baseline, even when letting each model have 40 different samples. A recent paper who was also written by Aman has found that this GSM 8K benchmark is actually a bit skewed, and that 50% of the numbers in the benchmark are one-digit integers. So we created a harder version of this data set that we call GSM hard, where every number was replaced with an up to 8-digit number. And here are the results. As you can see, all models, we have the direct approach. All models here use the same underlying model of Codex. They just use different prompting approaches. So the direct approach gives the model only the direct final answers to the prompt questions. Chain of thought is using Codex, and our PAL is the one that generates Python code. And as you can see, the direct approach and chain of thought have dropped by 63 and 75% compared to their own previous numbers. However, PAL has dropped by only 14%. So this shows how PAL is not only better at the standard benchmarks, it is also much more robust. And basically, because PAL offloads the arithmetic part to the Python interpreter, it's kind of robust by construction, right? It doesn't really care if the actual numbers in the question have 1, 8, or 20 digits. And since the Python interpreter is such a general tool, it is not limited to only do addition and subtraction, right? So far, we kind of underutilized the Python interpreter, but it actually can do many more things. So we evaluated the same approach on a class of a variety of other benchmarks for symbolic and algorithmic reasoning. So for example, if the question is, I have a chair, 2 potatoes, a cauliflower, a lettuce head, 2 tables, a cabbage, 2 onions, and 3 fridges, how many vegetables do I have? And the way we taught the model to solve this question is simply by creating a Python dictionary where the keys are the entities and the values are their quantities, and finally sum the values of the dictionary while filtering out the things that are not vegetables. So basically, the task of the language model is to convert the question into this format and also filter out things that are not vegetables. And I believe that both of these things are quite easy for a language model to convert into a fixed format and to tell which one is a vegetable or not. There's a quite easy tasks for a language model, but the final summation of all the values is delegated to the Python interpreter. So here are the results. As you can see, using PAL gets the results much closer to 100% than direct and chain of thought. And since and actually the Python interpreter is not limited to use only the Python primitives such as dictionaries and things and string and things like that. We can also teach the model to use external libraries. So for example, if 2015 is coming in 36 hours, what is the date 1 week from today in month, day, year format? In this case, we taught the model how to use the datetime and dateutil libraries by showing the model how to create an object of a datetime object that is initialized with January 1st, 2015, and then subtract 36 hours, and then add the relative 1 week to that object, and finally convert the resulting object to string. And here again, the PAL provides a very significant gains compared to chain of thought. So basically, the Python interpreter allows us to use external libraries as well. Yeah.
What is the difference between the text in blue and the red? Like is it all generated by the...
Yes, the text in blue is actually generated as comments, so the Python interpreter ignores them. But we found that in most tasks, it helps the model. The blue is basically chain of thought. If we kept only the blue lines, it's basically chain of thought. So we took the same sentences from chain of thought, but added a Python statement after each one of them. So except that we also taught the model to generate them as Python comments, so the interpreter will ignore them.
So like the entire thing is just turned into the Python interpreter?
Exactly. We give such input-output examples to the Python interpreter, and then for the test question, which looks only like that on top, the model generates this entire thing, both the intermediate steps and the Python statement for each of them.
Does it happen that there is like a compilation error, like a missing variable or something like that?
Yeah, sometimes it happens. Yeah.
So those are counted as failures?
Sorry.
Those are counted as failures.
Exactly. Yeah. Anything that doesn't lead to the exact accurate final answer is counted as a failure. Yeah. Another interesting question is whether this works with smaller models of code. So far, all the experiments that I told you about for PAL, we use the CodeDaVinci 2 model, which is the newest and strongest model of code by OpenAI. But we were wondering whether this requires a large model or can it work with smaller models as well. So we evaluated the same benchmark of the GSM-8K with the CodeDaVinci 1 model, which is the previous version of the same model, a bit weaker version that appeared about a year earlier, and the CodeCushman one, which is believed to be the model that is behind the Copilot plugin. And the blue curve is our PAL, and the green curve is chain of thought. So and the purple bars are the relative improvement between PAL and chain of thought. So as you can see, when we use a weaker base model, the results do decrease, but the relative gain of PAL over chain of thought remains kind of consistent across different models. So this shows that using PAL is beneficial in small models, but it scales nicely to larger and larger models. Another question is whether this requires a model of code or can it work with a model of text, such as the GPT-3 or the TextDaVinci series. So we evaluated the same benchmark, and these are the results, the same as the previous results using the CodeDaVinci 2 model, but we evaluated this again on the TextDaVinci 1, TextDaVinci 2, and TextDaVinci 3. So the TextDaVinci 1 and 2 are different varieties of the GPT-3. TextDaVinci 3 is believed to be the language model behind ChatGPT, but all of them are kind of designed for natural language. And we compared PAL with chain of thought, where the base language model is always the same. And here are the interesting results. When the base model is weak enough, or maybe its coding ability is weak enough, chain of thought does perform better than PAL. But once the model has a strong enough coding ability, PAL becomes better and better until with the TextDaVinci 3, PAL is better than chain of thought, and the results using PAL are close to the results using the CodeDaVinci 2. So basically, the conclusion here is that we don't have to have a model of code. We can use a model of natural language, but it needs to have a sufficient ability to generate code. Another question is about the prompts, as was kind of asked before. What is the importance of the exact design of the prompt that we provide PAL? So here are the results across two data sets. So this is a data set called colored objects, and this is a data set called dates. The blue bars are the standard chain of thought, the baseline. The purple bars are PAL, the full results as I showed you before. The orange bars are PAL without the intermediate steps. As you ask these blue intermediate natural language steps, we just omitted them and let the model generate only Python code. As you can see, this reduced the difference between the purple and the orange is the reduction in accuracy when we removed the natural language steps. So this shows that these explicit natural language steps are required. However, these orange bars are still higher than chain of thought. This is 91 compared to chain of thought, which gets 84. So this shows that maybe the even though we don't have explicit natural language steps now in the orange format, the Python program gives the model an implicit decomposition into actionable steps. Finally, when we removed variable names and we replaced every variable name with a non-meaningful random character, this reduced the results such that they were already lower than the baseline chain of thought. And we believe that using meaningful variable names, so for example, using variable names such as tennis balls and bot balls is very helpful because it allows the model to link the entities in the text with the entities in the code. And by not using meaningful variable names, it's sometimes hard for the model to track which variable refers to which entity in the natural language question. Finally, I'll show one last experiment. Another question is, what is more important, the code format or the Python interpreter? We saw similar decomposition before, but basically the baselines that we compared to use the code DaVinci 2 or the text DaVinci 2, but the point is that they didn't use an interpreter, and they used the chain of thought format, while PAL used both the interpreter and the Python format. So the question is whether the Python interpreter is actually needed. What happens if we just use the Python format without actually running the interpreter? So this is the standard PAL, when we let the model generate the Python program up to the computation of the variable answer, but then we print the answer using the Python interpreter. In the ablated version, we include this print answer and the final answer as part of the example to the language model. So the language model is kind of taught how to execute these kinds of simple Python programs. And then at test time, the model is also expected to actually generate the final answer. The bottom line is that doing so reduces the results by a lot. Even though the difference between the baseline and PAL is almost 9% of accuracy, using only the Python format without using the Python interpreter drops the results by a lot. And we believe that the reason is that as we hypothesize that the language models are not really good at actually doing arithmetic. So the Python interpreter is crucial. And the largest gain is provided by using the Python interpreter. So to summarize, and I hope we have a few minutes for questions. In the first part of the talk, I showed how given natural language inputs and structured natural language outputs, we can convert the output into pseudo-Python code and ask a language model of code to generate this Python code. In the second part of the talk, I showed how instead of expecting the language model itself to provide us with the final answer, we can teach the model to generate Python programs that will give us the final answer only once we run them on the Python interpreter. So basically, we offload the arithmetic part to an external Python interpreter instead of expecting the model to do something that it basically wasn't designed to do. I think that these two approaches raise a variety of interesting directions. So for example, in all the experiments that I talked about, we did the final execution step only once. We generated a Python program and then ran it only once, but nothing prevents us from taking the output of the interpreter and feed it back into the language model and maybe teach the model in some way to call the Python interpreter multiple times. Another interesting question is what other classes of tasks can benefit from this synergy between language models and external solvers. So we talked about common sense reasoning, mathematical reasoning, algorithmic and symbolic reasoning, but what other tasks in the world, in the reality, can benefit from using such additional external tools? I have a feeling that we didn't test it, that it's useful for any structured natural language task. Every natural language task that involves structure can benefit from converting the inputs or the outputs to Python code. And I know that people have talked to me about using these approaches for converting lab protocols and recipes and many different kinds of natural language texts that have some structure. Another direction is what other kinds of tools can a language model use in order to accomplish its mission. So a Python interpreter is just one tool, a very powerful tool, but maybe there are many other kinds of tools. I have a few examples, but I want to leave a few minutes for questions. So some of these tools can be retrieval from a database, a knowledge graph, or an API. Basically, all the models, all the OpenAI models are currently available as APIs that we can query and get the result. So if we think about a model as an API, we can think about a model that calls another model as a tool. So maybe a general purpose model can call a domain specific model only when needed. Or maybe a small model can process the input and call a larger model if it's not confident enough, or if the question is too complicated to be solved by the small model. So basically, all these compositions of models and tools are theoretically possible. Yeah, that's it. All our code is publicly available. Feel free to ask questions now or anytime on email or on our GitHub. Thank you.